Okay. So, hello everyone. Let me know if you can hear me, if the connection is good enough. Very happy to organize this event today. So far, we are 10 people, but more people should be coming soon. So, to introduce myself, I'm Melanie. I'm part of Pruna AI. Pruna goal is to optimize AI models to make them faster, cheaper, smaller, but mostly greener. So, the more optimized your model is, the less carbon emissions you consume. So this is why we are very happy to have Benoit today to talk about his work with Hublot and how GenAI can, what's actually behind the curtains. So it's going to be a presentation by Benoit. I will leave the stage, but I will look at your questions in the chat. Feel free to send them. I can answer that at the end of his presentation. He has amazing slides to show you, so he won't be saying you in the chat, but don't worry, your questions will be heard at the end of the presentation. Benoit, I'll leave the floor to you now.
Thank you for having me. I start the presentation quickly. So you see my slides and my slides only, right? Just to be sure. Melanie? Okay. Don't have any feedback. Yeah, okay. I needed to check the chat, sorry. Okay, let's start. So we'll talk about GenAI behind the scenes. So the infrastructures that are actually behind GenAI that are made of concrete, metal, heat, and vapor, among other things. Let's have a quick look at the agenda. I start with a very short introduction. Then we go to the topic itself that's made of 4 parts. The first one will be on hardware behind GenAI. The second part will be on the building, so the data centers themselves as buildings. The third part will be on the big trends, and the fourth on climate and environmental impacts. So as a first very quick introduction, I'm working for Hublot, and Hublot is a company that helps organizations in the social and ecological transformation of digital technologies. And we do that through consulting, through environmental impact assessments, studies, and teaching. And for myself, in a very quick manner, I'm a specialist of data centers and cloud environmental impact assessments. I'm an open source developer. I maintain one of the projects I work on is one which is an open source software to measure the energy consumption of servers. I worked in data centers before focusing on environmental impact assessments. And one of the projects I'm working on a lot these days is a prospective study on data centers, energy, land use, and water consumption in France. Prospective study that goes up to 2060 for ADEM with a group of people. And that's also in this context that I had to focus a lot on AI infrastructures. And so one of the reasons of my presence today. The first part regarding this presentation will be on energy, water, and hardware. And as a first step, I'd like to do an introduction note on energy and power, as sometimes there are confusions about them and the relationship between them. So maybe to clarify, power as a value is an instantaneous value. It's expressed in watts. So regarding power, we can talk about maximum power, we can talk about minimum power, average power, and so on, but it's different from the energy consumption. The energy is calculated on timeline and it's expressed in watt hour. So to illustrate that, on the following graph, there is an example of the measured power of my laptop on an hour. So if I look at the highest value on the graph, this can be called the maximum power, which is here a bit less than 16 watts. But if I want the energy consumption, I have to get the average power over the period. So the average value, the average power would be about 8 watts. And I have to take that into account on the full time scale. So as the period here is 1 hour, the conversion is very simple. It's a bit less than 8 watt hour. So that was to introduce the relationship between power and energy, and you will take attention to the units that will be used after that in the different slides, because depending if we talk of one or the other, that doesn't mean the same thing. So now the idea is to talk about the hardware behind GenAI, starting with the chips, GPUs that you may know of, for sure. So this first graph shows the evolution of the TDP of several generations of CPUs and GPUs. So the TDP stands for thermal design power, and it's let's say the maximum power that the chip and its package can endure before the heat is too high and can be dissipated. So it's an imperfect value, but it's still used most of the time to express the maximum power required by a chip. And what we can see on this graph is pretty clear, is that starting in 2019, a bit before the GenAI new wave, we got a huge increase rate of the maximum power for each new generation of chip. And because this graph is pretty old, the maximum data here are about 2020, 2021. This one extends a bit the curve. And what we can see is that the curve continues. So there is still a very steep curve on the increase over generations. And to clarify, the first graph stopped about the NVIDIA at the NVIDIA H100 level. And here it's about there. So now we have the GB200 GPU that's provided by NVIDIA, GB300, and now the Vera Rubin GPUs that have been announced more precisely this month, actually. And we see that the curve is very steep. And if you start with very simple comparison, so first a very French comparison, if you look at the maximum power needed for a machine that melts cheese for two people, it's about 300 watts. If you look at the maximum power asked for a microwave, it's about 1,500 watts. So about the same as 1GB300 GPU. So actually, this graph is also a bit outdated because with the recent announcement from NVIDIA, we know that the most advanced version of the Vera Rubin GPU, so the Rubin Ultra VR300, will have a TDP of 3,600 watts. So let's say that the curve continues to get steep. So now if we look at servers that will host those GPUs, in this example, I took a very average AI server, not necessarily the high-end AI servers you will find from NVIDIA or other vendors that will package NVIDIA products, but just to have some random AI server that will host here, it's 8 NVIDIA A100 GPUs. Its max power is about 5,000 watts, which is more than high-end oven. And it's 2 to 10 times more than a conventional server. So it really depends the kind of server, of course, but we are still in very different ranges in terms of power demand for AI servers compared to conventional servers. Oops, sorry. So the other element we have to take into account regarding data center electricity consumption trends is that this increased rate regarding chips maximum power is not an isolated trend. It's true for GPUs, it's true for CPUs as well, but it's also true for servers as a whole and not necessarily AI servers. If we look at non-AI servers sold, so those are the graphs in the bottom of the slide, whether they are low-end volume servers, mid-range or high-range servers, we don't really see the increasing energy efficiency that's promised by the industry. In those graphs, you will see there are 3 graphs in each. One is for the idle state of servers, which means the servers is plugged in, but it's doing nothing, basically. The second one will be for a 50% load, so which will, let's say, will work at 50% of its capacity. And the third one will be for 100% load. And we can see that the only state in which this improving energy efficiency over time of our generations of servers might be true is the idle state. So it's very interesting to see that we have this assumption, and I hear that a lot, that new servers will be more energy efficient for the same task. But if we look at data, as soon as you use your server, basically this assumption almost doesn't work in any case. Because we have the chips being more and more power intensive and the servers being more and more power intensive, it's pretty logical that the racks, so the full rack hosting the servers, will be more power intensive as well. And that's what we can see from Uptime Institute data over time. We see that the average power intensity per rack, so it's really large scale for all kinds of data centers. And it's not based on very classified data, it's big averages, but still it gives a trend over time. And we see that from 2011, it was 2.4 kilowatt per rack. And today we are more around 8 kilowatt per rack. So it's multiplied by 4. And the last data point of this graph is 2020. It's pretty old. And today it's probably more. And we need more data to assess that. But still, we see the increase. And to illustrate how this increase might be now, here it will be a pretty extreme example because it's based on new NVIDIA products, which don't represent the average rack that you will find in data centers, but still what drives these trends are those products. And so if we look at Blackwell generation of chips and servers and racks that have been sold by NVIDIA based on the Blackwell architecture, one example being the NVL 72 rack. The NVL 72 rack is based on GB200 chips containing about, I think it's 18 compute trays. It's a lot of servers and then a lot of chips inside them. And the maximum power of this rack is about 120 kilowatts. So you see the difference with the average rack power we had before. It's about 12 times the average rack that we might have now if we consider that we are around 10 kilowatt per rack. And to compare that to something more outside of IT, it's about 3 times what an average French household can ask for in terms of power, because in most households, if you ask for more than 9 kilowatts of power, then your electricity counter will just shut down the line. Those are already pretty huge values for a single rack. And it gets worse if we look at the new announcements based on the Vera Rubin architecture this time and the NVL 506 rack. It's still 18 compute trays, but now the maximum power is about 600 kilowatts. So it's 60 times the average rack that we have today if you consider it's about 10 kilowatt per rack, and 77 households if we consider the same comparison. And the next steps after 2027 might be 1 megawatt per from NVIDIA. There are already several articles talking about that. So now that we have talked about power, let's talk about cooling, because all this power, all this energy needs to be cool. The servers needs to be cool. And what we'll find most of the time in data centers is air cooling. So the principle of air cooling is very simple. You have hot coming out of the servers that is sent outside, and some air is cooled with chillers, then sent inside the room in confined alleys so that the servers can suck this cool air and cool themselves. This way to cool a server consumes a lot of electricity and it's pretty inefficient, but it's cost effective. It's really used by many data centers. They know how to manage that kind of cooling system. But the problem regarding AI is that it can't keep up with more energy intensive use cases. So because of that, what you might see in hyperscaler data centers, the bigger data centers, is cooling with the help of outside water evaporation through cooling towers. So this type of cooling system exists a lot in the US, not necessarily in France, because in France there are various regulations that prevent to use cooling towers. And this is a solution that can be more energy efficient than a full air cooling solution, but this consumes a lot of water. So it's about between 2 and 9 liters of water consumed for each kilowatt hour of energy. And when we do water consumption assessment, we make the difference between taken water and consume water. So basically, the water is consumed when it's evaporated. If it's a closed circuit and that the water is sent back to the local environment, it's not considered consumed. But here, with that kind of system, it's up to 80% of taken water that's evaporated. This technology basically is a disaster when the local area knows water stress already. And that's because of that you might have seen in the media many news titles about AI consuming a lot of coming from data centers that use that kind of technology. So the thing about it is that it's a local issue. Building a water intensive data center in the desert of Nevada doesn't have the same impact as building it in an area that doesn't have significant water stress. And the thing is, a lot of data centers are built in those stressed areas. And we will see one in a few slides. To be more complete about AI cooling, there is still another issue, which is a physical constraint to cooling, which is if you have racks that are up to 40 kilowatt per rack in terms of power intensity, it's okay to use air cooling. It will work. But above 40 kilowatts per rack, you physically need to change the cooling system. You have to go for liquid cooling. Between 40 kilowatt per rack and 70, it might work with door cooling, which is an intermediate system that relies on liquid cooling, but the circuit stops at the door. And then the air that's cooled thanks to the liquid cooling system is pushed inside the rack through fans. And after 70 kilowatt per rack, you will need direct liquid cooling, which means direct liquid cooling to chip. You will need to have contact through a surface that's directly on the chip itself. To distinguish between door cooling and direct liquid to chip cooling, direct to chip might look like this. You will have pipes inside the server that will get the liquids up to a surface that's directly on the chip. And regarding door cooling, it will be just special racks with doors that are connected to the liquid circuit. But then it will be air that will be sent to the servers themselves and not liquid pipes. So the thing is, before the last few years, with the new wave of GenAI, most actors of the data center industry were used to air cooling and water evaporation. So in many cases, they didn't plan for direct liquid cooling. And as a result, there are some projects of even hyperscale data center that didn't fit GenAI power intensity and also the associated cooling requirements. For example, Meta had to demolish an entire building under construction to apply a new design, providing more energy intensity for GenAI. And it happened in a 4 years time frame. So the time scale is very short compared to the lifetime of a data center or even just the time needed to build a data center most of the time. So now if we try to have a look at what's inside a data center and what it's made of. So in the bottom, you will have, of course, the IT rooms where you have the server, the racks, part of the cooling system. But it's not the only room. You will have, let's say, other rooms that are dedicated for energy supply material. So you have the UPS that are the uninterruptible power supply that are machines responsible to ensure that you have a constant power supply, even if there is an issue on the main power source. The main power source being transformers that you will see in the back, but those UPS will be connected to batteries. That's why it's in a separate room because batteries can take fire. So you don't want to have them in the IT room. And so the batteries can be used as a second energy source, but it's very short in terms of capacity. So you won't run your full data center on several days with batteries. It's more minutes or hours in the best case. And you will have to switch at some point. If you have an issue, you will have to switch on the third power source. That will be the backup power generators that you see in blue in the back as well. And those backup power generators, they are run with gasoline, they run with fuel. So it's most of the time it's completely based on fossil fuels, even if it's supposed to be very occasional that we use those backup power generator, they are very impactful when we use them. So now the idea is to have a look at the buildings themselves in terms of size, in terms of land use. The buildings, they might be of very different sizes. So from very small data centers up to 100 square meters to very big data centers that are bigger than 10,000 square meters. So there are several classifications existing either in European official documentations or industry. But what you have to think about is that the data centers we are talking about for AI, in many cases, they are more on the right side of this chart. And very big data centers, just to illustrate, a data center of 10,000 square meter is about 3.5 times a soccer field. And some of them go way beyond 10,000 square meter. So the idea here will be to have a quick tour of two kinds of data centers. I hope you will see my screen properly. This one is let's say it's a medium data center that's in Lyon in France. What you will see on that kind of data centers is the visual of what a typical air cooling system will look like. You will have fans on the outdoors that will just throw out the hot air. And it's a building that kind of looks like office buildings that might be around. So in many cases, it's not that obvious that there are data centers. Often they are very hidden in the urban landscape, which is very different from very big data centers like this one. So this is a data center in Vegas. So this is a hyperscale data center this time. We know it is used also for AI services because it's one of the data centers used by CoreWeave, a GenAI infrastructure pure player, many other. And what's interesting in that kind of data centers is the shape, which is more long than large, let's say. And another item that's very interesting is that it might look like a typical air cooling data center as well because we see fans, but actually those items here are not typical air cooling fans. They are water evaporations items. So there are fans that will expel vapor in the air. And it's very different from the cooling towers that we have seen before, which is interesting because the cooling towers, as you have seen, are very obvious. It makes a lot of vapor in the air. So it makes very good photographs if you want to have a nice picture for a newspaper article. And those items here, they are much more discreet, much more hidden, and much smaller also. And those are the kind of evaporation system that we see now, and we see more and more, while we see on new constructions, we see less and less evaporation towers. And so to have a grasp on the size of the data centers, because, first I forgot something, that I show you this data center, but if I zoom back, this is actually a campus. It's like a campus of data centers that are about the same. And there are 1, 2, 3, 4, 5. Yes, it is. I think there are like 8 or 9 data centers of this sort in this area. And it's in the Nevada desert. So as we said just before, in a very water stressed area. So having evaporation systems in that area is a real problem for water stress. And to have a grasp on the size, so I will get back to the presentation. This data center is about as long as the Eiffel Tower is high. So it's 320 and it's about 19,200 square meters, which is roughly 7 times a soccer field. What we didn't see in this, because it's just elsewhere on the area, but what we didn't see in this overview is that on many big data centers, there is also an electric substation that's dedicated to the data center that's directly on the same field. I just point this out because regarding this topic, it was a bad example. But you will often see this if you look at Google data centers, Meta data centers, you will find dedicated electric substation and transformers directly on the field. And so to get an idea of the power asked for big data centers, I tried to put here a quick comparison between different data centers and their power. So the average French data center, so it's an average among all the data centers in France. So data centers that are smaller and data centers that ask for more power than that, but an average would be about 7.5 megawatts. A big data center, at least in France, we would call that a big data center, is 100 megawatts. An hyperscaler, probably like the one we saw, would be about 200 megawatts. And the GenAI dedicated data centers that are announced both in the US and in France. So in France, we had several announcements for data centers of 1 gigawatt or 1.5 gigawatts. In the US, there were already announcements for 2 gigawatts data centers. And so just that we see what it means compared to the first ones, it's like just 10 times what we would call a big data centers or a big data center already. So there are many hypotheses on those new big data centers because it's very hard to, especially in France, it's very hard to deploy 1 gigawatt data center just like that. Most of the time it's planned in many steps. We'll ask for maybe 40 megawatt, then 40 megawatt, then 40 megawatts, and at some point add up to the total. So it raises a lot of questions because we are not used to see such data centers, but we are not used to deploy such power demand in a such short time frame because some of them are announced for like 2029. So it's very short. And just to get a grasp on it, like 1 gigawatt of power is a bit more than what a nuclear reactor can produce, which some nuclear reactors, for example, are about 800 megawatts, capable of producing 800 megawatts. So looking at big trends regarding data center electricity consumption before the GenAI push about that, think based on the synthesis made by the International Energy Agency in 2024, it was said to be about 300 terawatt hour in 2020, to have doubled from 2020 to 2024, to be up to 1.5 times higher from 2024 to 2026, about 600 terawatt in 2024, which is about 1.3 times what France as a whole consumes in terms of electricity. And it was said that it might be around 800 in 2026 and up to 1000 terawatt hour in 2026 in the worst case scenario. Take attention to the fact that this graph includes cryptocurrencies, while the more recent evaluations don't. So there is a slight shift in the perimeter between this slide and the next one. Trends that we have now, so during the GenAI push, there are a lot of them. Estimating the global electricity consumption of data centers or of AI is a complicated task because you have to deal with many hypotheses, many uncertainties. But still, what we can see from all those estimations is that for AI itself, so just the electricity needed for AI, and not talking about the other data center use cases, so just for AI, today we are about several tenths of terawatt, and in 2030, we might be up to several hundreds of terawatt. That those are the order of magnitude. And regarding the global data center electricity consumption here without cryptocurrencies, so that's the tricky part for comparing the previous estimations and those ones. It might go up to close to 1000 terawatt hour in 2030. And one of the insights from the latest EEA report is that in their estimations, around 70% of the growth in electricity demand for servers between 2025 and 2030 would come from accelerated servers, more or less GenAI servers. So regarding climate and environmental impacts, before we talk about greenhouse gas emissions that are associated to data centers, there is a thing that's very important to know, is that the greenhouse gas emissions of data centers are, that we know of from the big tech companies, are very opacified. They are blurred, basically, because thanks to an accounting technique, which is buying green electricity certificates that will assess that 1 MWh of electricity consumed comes from electricity produced by renewable energy means of electricity production, you can remove from your carbon footprint most part of the carbon footprint of your electricity consumption. So this mechanism exists. It's used by very many companies, up to a point that the Guardian estimated that for an average on all the big tech companies, it's like greenhouse gas emissions due to electricity consumption of data centers are 600 times higher than what they announce. So for Meta, it's 3,100 times higher. For the other big tech companies, you have the trends here. As an average, it's 600 times. So just using this mechanism, we actually don't have a good overview of the current greenhouse gas emissions for data center electricity, not for the rest of data centers. And we have to add to this that in the US, more than 56% of electricity consumed by data centers come from fossil fuels. So when you see big tech announcements on green energy and renewable energy used for the data centers, the hard truth is that 56% of electricity consumed comes from fossil fuels still. And this is without taking into account those green energy certificates that will blurry the global image. Second point is that Google and other big tech, we'll talk about that, show a huge increase of of greenhouse gas emissions in the last year. So for Google, it's plus 50% over the last 5 years. And we have to precise also that Eric Schmidt said that AI will solve climate change anyway. That seems it's not an issue. Microsoft shows an increase of 30% of greenhouse gas emissions from 2023 to 2024, mostly because of GenAI of concrete used for data centers. And in the middle of all that, the scope 3 emissions, so everything that's not related to electricity, but that's related to manufacturing, transport, end of life of materials in the data centers, those emissions are overlooked. And yet, in many cases, then they really can be the biggest part of the emissions. So if you add up all those numbers, the big tech decarbonization, which was the trend before the Trump era, now it's a bit less trend. It was a very messy trend that was announced and not a very clear one. Now, what we see is an increase in the detachment of the big tech from actual climate action. Regarding data centers, Meta announced a very huge data center. I think it's 2.2 gigawatts, only powered by fossil fuels. And it was last year. There are many other examples of data centers and AI data centers based on fossil fuels, but actually directly using fossil fuels, not just using a pretty brown electricity grid, using directly electricity production means based on fossil fuels. So it's also extending coal plants on the current grid, and can go on and on with the examples from Elon Musk XAI data center that's using gas turbines that are actually illegal because they didn't have the permit for them, but they still use them. So we see now that we went from the climate action ambitions showed by the big tech, and now we are in a time where the big tech don't even hide themselves from using fossil fuels actually directly for data centers. what we have to take into account here also is that we just talked about greenhouse gas emissions, but this is only the tip of the iceberg regarding environmental impacts. Most of the time, people who discover what environmental impacts of ICT, but also of AI are, they go through this process. They start with electricity and water. Then they go to greenhouse gas emissions. Then they realize that there are actually up to 16 environmental impacts criteria that we could look at. And it's just the ones that we know how to assess. And then they realize that all of those are just first order impact, and that AI systems and digital systems have much more impact through second and third order effects, which are not direct impact, but the impact that the system will have on the economy or on the behavior of users. For example, I will go to the example after that, just to illustrate the multiplicity of the environmental impacts. I don't know if you know the planetary boundaries model. It shows all the thresholds that we shouldn't cross so that humanity is not in danger, basically. So climate change is one of them. Today, it's estimated that 6 or 9 planetary boundaries pressured. And if we look at AI, this is based on publication from Sophia Falk, who is working at the University of Germany. On the right part with the arrows, you have the planetary boundaries that are pressured by AI. So you see that there are 6 of them. So it's not just climate change, but it's also biosphere integrity, land system change, freshwater change, ocean acidification, and novel entities introduced in the environment. When we talked about second and third effects of AI, of course, many people will say, yes, but AI can help the environment on several topics because we can, for example, we can track illegal fishing in protected areas thanks to AI. That's a project that exists. We can look at the impact of the banks and the insurances that are actually helping new fossil extraction projects. That's also a project that exists. So yeah, we can do great things with AI, but the real question is what's the most part of the usage we have for AI? And what I want to introduce to you is what Will Alpine is talking about. He is a former Microsoft employee who worked on OpenAI. And he did a quick comparison between the official greenhouse gas emissions from Microsoft in 2023 and just 2 projects that Microsoft provided to his customers, which were Amazon and Chevron. And those projects were AI projects, obviously. They were basically here to help optimizing fracking and extracting fossil fuels from the American soil. And so the impact of those 2 projects exceeded 3 times the Microsoft global greenhouse gas emissions. And that's really the key takeaway here, that AI is being used to keep hooked on fossil fuels much more than to get us off fossil fuels. And I hope I wasn't too long. And thank you. Melanie, are you here?
Hey, I'm back. So, talking to the chat, is there any question you want to ask to Benoit? And if you're ready to talk, please share as well. There's some typing. Just like typing still. Don't be shy if there's any questions, and that might seem silly questions. I spend your yeah, that was a very cool presentation. Thank you very much, Benoit. If anyone wants to share the slides that they found the most interesting, or if there are any information you didn't expect to see, share your highlights as well on the presentation. Oh, thanks, Sonia. Yeah, the data centers pictures were great. Benoit, that's a good find. Yeah, I think there I'll let you a few more minutes if you want to ask questions and share your feedback. Thanks, Amin, as well, and for the feedback. So the talk is recorded, so we'll share it on our YouTube channel very soon. Benoit Benoit, where can people contact you after the talk if they have more questions?
Yeah, I will just add up on the last comment from Marco. He was talking about OpenStreetMap. So yeah, that's for sure a better alternative to Google Map, but I prepared my presentation on Google Map. But just to say, on OpenStreetMap, you have a very nice project, which is called Open Inframap. I don't know if you know this one, but you will have access to positions of data centers and critical infrastructures like electricity, power grid items on OpenStreetMap. So if you want to have a look, that's a very nice resource. And one of the projects that we have in the study we are running these days is to feed these data sets with the data that we have collected for the studies, which means power, which means PUEs, WUEs, and other metrics.
Awesome. And there was a question from Bruce about the last slide. Is there any framework to assess second and third order effects?
So the thing about second and third order effect is that it's not always, you can't always put numbers on them. So most of the time what is done is more qualitative approach where what you try to identify are the positive and negative trends, the positive and negative dynamics that will lead to either being better or worse for the environment. So this will look like it's called consequential graphs. So basically those are graphs that will represent if I deploy that kind of system, it might have an impact on the user's behavior that looks like this, and that will be either positive or negative on the environment. And you draw all the consequences, and then you try to have a qualitative approach on, as a whole, is this system positive or negative in the end? So that's not the only tool, but that's one of the tools that I know of. But it's a bit different than what we are used to with direct impacts, which is about quantifying things.
Awesome. There was a question from Sonia. Can you recommend cloud providers that are a bit greener? And she missed the beginning. So did you talk about the impact of material extractions in order to build data centers and produce chips?
So first question, to recommend cloud providers on tiny differences, we might try to do a comparison. There are some articles on the Boa Vista blog that talk about it, but it's pretty hard because so one metric could be how many data centers do they have? Because building a data centers is massively impactful. AWS has the most data centers, so we could say, okay, it's the worst. That's a biased approach as well. And so the core problem here, I think, is that the cloud business model has an issue. The cloud business model is made to ask for more demand, to ask for more systems, to ask for more consumption. So even if they are more optimized at the data center level or at the server level, let's say one cloud provider might be better than another. On a big scale, if you look at the absolute impacts, it's very hard for a cloud provider to be actually green, if that means anything. So sorry for that not actionable answer, but I really think it's important to keep in mind that we have to think about the whole system and not just optimizing, like choosing a better provider is a good approach in itself, but just it's not enough. And did you talk about the impact of material extraction, impact of concrete? I didn't talk about it in details because it's a huge topic in itself and I wouldn't have the time. But yeah, that's a big issue, especially the GPUs. The GPUs are very impactful to manufacture, or at least we think they are because we don't have any data. So they are impactful because they consume a lot of energy. This we know, but we are still waiting for actual good data on chips manufacturing. There are two projects I know of ongoing. So we might have in the next several months publications on the impact of GPU manufacturing. But today it's a bit complicated to answer those topics.
Interesting. There's a question from Suren Duran. Are there any green data centers or carbon offset programs being used to reduce emissions from AI development?
Yeah, the green projects, you will find many. Green projects that are actually green, it's harder to find. So there are things that are good things to be made. For example, if a data center is running AI, using DLC and using direct liquid chip cooling is necessary and is a good thing for the environment in some way because you will be much more effective at catching energy lost. Actually, you could then be more effective in providing the generated heat for other uses, which is a thing that's very famous now. We talk about data centers that will help to heat a pool or to heat residential area. But actually, there are very few data centers that actually do it. With DLCs, it could be a bit possible to do that. But again, we are on optimization here. And the real problem is the massive volume of data centers that we are planning to develop. And carbon offset programs, there probably are. Carbon offsets are like one of the most, it's a wrong friend. Like many companies rely on them. Problem with carbon offset is that you can have double counting through accounting mechanism. You can have two companies that are offsetting 1 ton of carbon with the same mechanism, with only 1 ton of carbon actually captured somewhere. You have many issues with the system because it's a market system. So it's not made to be effective in an environmental point of view. It's made to be effective in a business point of view. So I wouldn't recommend that way to make the situation better.
Okay. And a final question before we close, we already passed the time. From Marco Polo, are you in contact with the collective Lineage Gestion? They are collecting info and putting them on OpenStreetMap.
Not directly in contact with them, but I know their action because we looked at what they do for the study. And at some point when we will provide the data we have worked on for the study, I would like to connect with them. So that's a nice preparation. Thanks.
Awesome. Thank you everyone for attending the talk. Again, there will be a recording on YouTube very soon. Thank you, Benoit, for your presentation. That was awesome. And if there is any idea that the crowd wants for a next talk, Pruna, we want to do more talks about green AI and sustainability. If there is any topics or speakers you want to submit, feel free to contact me or someone at Pruna. Thank you, everyone. And have everyone a good evening or day if you're starting your day. Bye-bye.